Thank you. Thank you very much for the kind introduction. So this work, part of this work has been done in collaboration with a colleague of mine, Dr. Jim Martin, and also Dr. Richard Brooks at Clemson University, that we collaborate together on this NSF grant. But what I'm going to talk here about today is a little bit different from what we're hearing so far. And in particular, looking at connected vehicles from the point of view of security and therefore basically resiliences against cyber attacks. So what we have is that we know that we have a lot of opportunity with connected and automated vehicles. We have the possibility to improve traffic throughput, safety, fuel economy. But what we, especially if we forget, we also have potential vulnerability associated with the use of connectivity. And we focus mostly in this work that I'm presenting on cooperative data cruise control, but some of this activity then have been extended by me and some of my colleagues into more general cases for distributed CPS, network CPS. So there are several V2X applications and that are being studied, for example, for road safety, collision warning, collision avoidance, intersection warning, for traffic management, such as speed management and traffic information routing, infotainment, and also autonomous driving to really control the vehicle from the point of view of, for example, fuel economy or braking or cooperation with other vehicles to improve overall traffic flow. But together with those, there is a whole set of other issues coming with it, which are security issues. And there are several types of attacks that can be implemented on a vehicle network. Yeah, in this work, I mainly focus on the one in the box, which are associated to availability of the network, and in particular, focusing on jamming and denial of service attack. But in the past, I've been also done work in integrity and data trust, and you can find that work on my website. So a little bit of a review. There are, of course, sophisticated threats that can be implemented. And the problem is that the cars are on the road and they have to satisfy certain safety requirements, which are different from other applications, such as where you can have use in a computer network, okay, or in an electric grid. And so here we have, people have trying to find solution to this problem, more or less traditional approaches. And but there are some key aspects that still needs to be really nailed down. And first of all, security must not come at the expense of performance. So whatever we do to ensure security must not reduce the performance of the system. Otherwise, people will not be likely to utilize those vehicles. And if we have the traffic safety conditions, then the security does perform in real time, right? We have a system that is moving and with passenger, and they may be at risk of collision, for example, or injuries. And we cannot wait, right? We do not have the luxury to wait for like a virus scan to tell me, oh, there is something wrong with the system, please shut down. Okay, no, that's not possible. The other problems are that we cannot, for example, queue the messages, right? Otherwise, we will not be able to react on time to certain conditions. And of course, there is the problem of certification. How do we ensure that there is a certifiable security? How can we launch an attack on a system like a car? So there are basically a couple of ways to do it that are well known. One is through the network communication. For example, you can do network flooding that affect the availability of the network. Or you can do, for example, a more integrity attack in which you are modifying the packages that are flowing through the network. All the other aspect that you can do is to go on the vehicle itself, and you can hack sensor and actuator in the vehicle. This can be done at the body shop, for example, or you can affect the CAN bus reading by overriding the messages in the bus and affecting the high-level control. And some of the vulnerability, for example, are potentially through the infotainment system and other type of systems that are on board of the vehicle. In some of my previous work, I have used some more traditional approaches to solve this problem. In particular, for example, the denial of service and the packet dropout. But these approaches have some limitation in which, for example, require some assumption. For example, for the packet dropout, we need the Bernoulli distribution, or we need to be able to estimate the delay in the case of denial of service, which they are not in most of the cases are difficult to be met. So here, what I'm going to talk about is a different type of approach that we have developed that is basically a more sophisticated in a sense, but utilizes hybrid modeling to really address this problem in a more formal way. And I'll start first by here with the cooperative data squeeze control, traditional approach, and just a comparison with the ACC. And so in the ACC, we just have using the information from the sensors and without communication between the vehicle. And the objective is to maintain a certain relative distance from the vehicle, which depend on the highway constants, headway timing constant, H, and initial potential distance R. And the idea is to send this error to 0 and possibly have a certain condition for string stability. Now, in the cooperative data squeeze control, we have the injection of information to the communication network. And in particular, we are focusing on a particular scheme here, in which the preceding vehicle sends the information to the vehicle follower. And there are several other schemes out there, but this is the one that we mostly focus on. This is one of the most popular ones. And the information that is sent in a V2V fashion is this UI-1. So it's the control action of the vehicle in front to the and is sent basically to the network to the real vehicle in such a way that you can basically improve the control in the vehicle that is following. Now, the issues arise when we introduce, phenomena that are typical of network communication, in such a way that we can have delays, or we can have variable time sampling. And so this really makes things challenging. And the question is, how can we deal with this phenomena in our model? So here is the way that we model the problem. We made some assumption on the variable transmission interval, which is bounded by this maximum allowed transmission interval, which is a TMATI, and the network delay, which are also bounded by TMATI and the maximum network delay, which is this TMAD. This is to ensure that the output is received by the controller before the next sample is sent. And what we basically do is we model the system in such a way that the whole platoon is considered as a cascade of dynamical system. And we want to design things in such a way that we have both performance of each vehicle independently and also string stability. So here is what happens. So at a certain time step, let's say T0, the control input of the vehicle, leader vehicle, let's say, is a sample, and a packet is created. The packet is then sent to the network, which has delays, and then is received from the vehicle follower, which update is value you had, which is the value stored in the zero order old block. And the system basically can be represented as a linear system with jumps. And it is clearly amenable to be described as a hybrid model. In particular, what we did is we follow a hybrid system framework that is being proposed previously by Goebel, Sanfelice, and Thiel. And we enlarged the state space with the auxiliary variable, which are subject to a reset. In particular, we introduce variable SU and L and a trigger, time network trigger tau. So what happened is basically when the information is sampled and the packet is created, then the variable SU is storing now the new value. Then that value is sent through the network, and there is after some delay, it is received on the receiver side, and the value of the zero order old is then updated. And the variable L basically keeps track of the fact that the next event is either a sampling event or an updated event. So here are the requirements that we have for the design of the control. One requirement is that we need to guarantee string stability. And the second requirement is a individual vehicle stability, in which we wanted to keep a desired relative distance. And we basically introduce a particular way to deal with this. The local parameter that we have to act on are this controller parameter KP and KD, which is the traditional controller parameter of the CACC. And we basically define a region in which we want the eigenvalues lambda of the system to lie. Okay, so we have two possibilities here really that we are looking at, since we have only three eigenvalue for the system. One is that we have one real eigenvalue at lambda m, or we have two complex conjugate eigenvalue at lambda m, and the third one is inside the gray area. Okay, so what we are trying to do is to solve the following problem. We have platooning parameter H and tau D, and tau D basically describe a little bit the dynamics of the drive shaft of the vehicle in a very simplified way. And we want to design the parameter KP and KD of the controller in such a way that we satisfy the condition P1 and P2, which are string stability and individual vehicle performance, with the larger possible delays and intersampling. So that's basically the idea. So what we did in our design approach, we have sufficient condition for the string stability, and that allow us to estimate the trade-off curve, combined with a necessary sufficient condition on the controller gain to satisfy the performance requirement. And what we come up with was a tuning algorithm, which is a more computationally efficient algorithm to solve this problem than the existing ones. So in order to solve the string stability problem, we develop sufficient conditions that are expressed basically by solving this LMI. Now, the problem that we have here is that this LMI is nonlinear in the controller gain, which are embedded in the A11 matrix. And the gamma parameter is the parameter that the smaller the gamma, the higher will be the delay and the transmission interval that we can handle. So the way that we address this was to take advantage of the particular structure of our system, and in particular the two conditions that we have, condition C1 and condition C2, which basically allow us to express KD as a function of KP through the characteristic polynomial of the system, and to define a range for KP. And with this, we had developed basically, we solve basically for finding this necessary and sufficient condition. And we have performance that are constrained by the powertrain time constant. So lambda m cannot be as small as I like, but there are some constraints there. And we have the relationship between KD and KP, which allow us to reduce the number of variables that we need to use in the solution of the LMI, because now we have a relationship between KP and KD. So instead of having a problem that has 2 degrees of freedom, now we have only 1 degree of freedom. So the problem that we basically solve is to minimize the system, the gamma, subject to this matrix inequality and this performance matrix. And so we do is an algorithm that look at both cases, case 1 and case 2, and find to a grading the minimum KP, the KP such way the gamma is minimum, and then we compare the two values of gamma and we select the KP accordingly. Then from the relationship between KD and KP, we can find also the KD. So here is what we have obtained for a particular case that we have a comparison with the more classical plot work, which is really a seminal work on CACC. And what we see is that the algorithm, this standard CACC algorithm provided by Ploy, basically the value of gamma and KP is defined by this blue rectangle here. And what our controller does is to find new values such a way that the system is actually able to handle a much wider range of TMATI and TMAD. So as you can see, there is a substantial improvement in the system ability to handle delays and variable transmissions. And from the simulation, you can also see that the performance, it is not deteriorated. Actually, the performance is improved with respect to what the plot algorithm will do. The plot algorithm, so here we did the simulation at the top point over here, where we have 150 basically millisecond, both of transmission delay and network delay, and transmission interval. And so in that case, we can see that the system from Ploy will not be basically string stable, and but our system it is, and it behaves very nicely. So in the next slide, I have here a way to show this in a simulation. So if you look at basically the red one are the one that have the new system, new controller, and the one in the blue are the classic one. And so you can see basically now when the system is going to break, that we have a very nice smooth behavior for the case of the red, and the blue ones is oscillating, so it doesn't have a very stable behavior. Okay, now the next step would be, how do we deal with the denial of service attack? The effect of denial of service attack in this case is potentially the one of creating a disruption in the communication. And we have some assumption that we have introduced. we have potentially radio jamming that can be performed by an attacker in an unknown way, so there is not a known strategy for it. And but is the energy and geographic constraints. So the attack has to be happening, in a limited region, as is reasonable that the vehicles are moving, and therefore, when they come into the range of the attacker, they may be under attack, but then they drive away from the region, and the system will be restored to the original status. So there are then issues that we need to address in terms of string stability in the presence of this attack. And here is still a comparison between ACC and some standard CACC approach that is trying to have a fail-safe mechanism when there is an interruption in communication, for example, to switch to standard ACC. But what we have here is that when we have a cooperative adaptive cruise control platooning, the inter-vehicle time gap are much smaller than, for example, ACC. So there is always potential issues in terms of safety that when you're trying to switch, you may be too close and the system may not be able to react quickly enough to avoid collision. So here we have two research questions that we're trying to address. First one is what net vulnerability and DOS attack can we tolerate without the need of a fallback strategy? And how do we design the CACC in such a way to maximize the network resiliencies under this attack? So here is the structure of the system. Now that we are looking at it, we have no delay in this case, but we look at having intermittent communication. So basically you can have failure in transmission as represented by this picture at the bottom. And delta is our resilience matrix. Basically, it is the maximum allowable number of successive packet dropout that we are able to handle without having stability issues in the system. So the way that we solve this problem, again, that we formulate in a similar way the problem that we saw before, but now the objective is to maximize this delta. So we have a similar procedure that we did, similar to the one that we did before. So again, we have the two conditions that we have potentially either fixing the real part of one eigenvalue to lambda m and the other two to be complex conjugate, or condition 2 in which we have a 2 complex conjugate eigenvalue at lambda m, and then the other one is inside the gray area. And in this case, we need to solve a slightly different LMI. And again, we utilize the constraints that are from KD and KP to reduce the number of variables. The problem is, again, non-linear. And so, but once we basically grid with respect to, for example, KP, then the problem becomes manageable using conventional tools. And so what we do then is, again, solving now this problem with these different LMI conditions. And we are able to determine a new set of gains that provide resiliency against certain number of packet dropping. And here is the comparison again with the Ploy work. And here you can see the poles of Ploy versus our. And the condition that we are getting here is that we are able to handle up to 5 consecutive packet dropping with our strategy, where Ploy can only handle 1. So that's kind of the results. And again, I have another video here that shows clearly what happens in the system. So the blue one, focus on the blue one, and you will see what happens when there is the dropping happening, and the system that is deployed one is the blue one, and the red one is the one with the new strategy. So you will see that the red one behaved very nicely, but the blue one almost looks like it's crashing against the vehicle in front. Really, the behavior of the system clearly shows some kind of instability. And if you have a much more number of vehicles, definitely you will have a crash. Okay, so until now we have made the assumption that we have a device which is a holding device at the controller, which is this zero order hold device. But now the question can come out is, okay, but since we have this loss of sample, what if we replace this zero order hold device with a more general device, which has some inter-sample dynamics? We'll be able to improve further on the previous results. So what we did is we introduced a inter-sample dynamics that's a more general form, and that results in a change in, of course, the LMI that we have to solve, but we can still handle it. And by looking at what we have now with the new inter-sample approach, we get one extra sample that, so basically we can handle 6, in this case, packet dropping in a row, one more than the previous controller. So it's a small improvement, but yes, there is potentially an improvement in doing that. So we did basically also a comparison by using different time gaps, and what we did see is that, generally speaking, the inter-sample always guarantees a higher resilience than the zero order hold. So, okay, so that was looking at the DOS with the causing the packet dropping, but also DOS can cause combined phenomena. So the denial of service attack can not only cause packet dropping, but it also can cause delay. So what happens is we need also to consider the effect of the delay and how much delay can we tolerate before things break down. And so that's what we did in this next work. So we then reformulated the problem a little bit because we had to deal with the delay. So we kind of combine the previous two works together. And now the problem was to basically find a new Lyapunov function that will allow us to deal with the trying to find basically sufficient condition for the solution for the problem. And of course, we have to have a decrease at the jumps and also decrease while flowing. So we're able to solve this problem in a similar fashion once we found the correct Lyapunov function. And that was the result that we got. So, to here we have the Ploeg. Ploeg is able to tolerate only one packet dropping with a certain amount of delay, while our strategy is able to basically handle same amount of delay, but a larger number of packet dropping at the same time. And if we replace the zero order hold with the intersample, we get an additional packet dropping that we can tolerate. So this kind of, provide an idea of how things can be designed in such a way that we can guarantee further robustness. And notice that we didn't make any sophisticated changes into the controller itself. Really, we have retuned the gain of the controller in such a way that we improve the overall performance of the system. Okay, then what we did is we went from this particular application to vehicle platooning to a whole new set of application, which a more general class of system, which is a network control system. And basically, what we did an analogy between what we had in our vehicle model and a more generic network control problem. And basically here, what we look is now a more general problem in which we want to design a controller and design an holding device such a way that we have some guaranteed performance under network delay and variable transmission. And here what we look is basically to design a output feedback controller, and utilize a holding device in order to deal with the problem. And what we had is we first divided the problem in two parts. So part number one, we look at computing some trade-off curves. So we assume that we have controller and holding device, and can we find what are the trade-off curve between the transmission interval and the network delay, such a way that the system is input to output stable. And then we work on a control design problem in which we have a co-design of controller and holding device such a way that the system is input to output stable with the largest possible transmission interval. So there are some challenges that we have to address to solve this problem. Of course, we have, first of all, to find a good Lyapunov function in order to solve the problem, which is a clock-dependent Lyapunov function, because we are trying to model the system as a hybridodynamical system. And we need to be able to guarantee decrease during flow and decrease at jumps. And we have to deal with the conservatism of the trade-off curves. And what we add is, of course, the problem then becomes a problem to be solved in some kind of linearization of matrix inequality. And we need to find basically stability conditions and control parameters for this. So here is the way that we model the system in the case of computing this trade-off curve. And so we have storage aerodynamics, and we have this time trigger that keeps track of the transmission, variable transmission delay, variable transmissions. And what we did is we found a Lyapunov function suitable to describe the problem and to solve the problem, basically, and conditioned on sufficient condition for having a decrease at the jumps and a decrease during flow. So the proposed solution, basically, in this case, is conducting a line search over this parameter delta and exploiting some convexity condition on the matrix inequality. So here is we apply that to a different problem now. This is a batch reactor problem. And basically here we have the two cases showing. So basically we have the same problem that was solved by Emmels and Altry and it shows that their approach provide less conservatism in terms of transmission intervals. So with their approach, they're able to handle larger thematic. Our proposed approach is instead able to handle larger delays. And so, our approach also can account for intersample dynamics. The other problem that we have been addressing then is the one of co-design. And so can we now co-design K and J, so the controller and the intersampler, in such a way that we have some better property for the system in terms of being able to have the maximum possible, for example, delay that we can sustain the system. And here again, we model the system using a time trigger and using basically a hybrid formulation. And again, the challenge is to find a suitable Lyapunov function that can be used to find the stability condition through matrix inequality that then they need to be solved. And the controller and holding device actually are exploited in such a way that you actually facilitate the solution of the matrix inequality. So the approach that we have adopted is a kind of a reminiscence of input to output state stability. And here is basically the way that we look at the system in a closed loop form. And what we did is basically we found a Lyapunov function, which is a combination of this V1 and V2, and a condition that guarantees basically through this Lyapunov function the overall system to be stable. And then we apply this to a very simple case. This is just a a double integrator just to see basically what happens, but with basically delays, and in this case a value of thematic equal to 0.39 is obtained by design. So on this basically conclude my presentation. What I want to do is to thank the National Science Foundation. This work was basically sponsored by grant in the CPS program. And I want to thank my former students, and now is graduated, and it is at MathWorks, working at MathWorks, and my collaborator, Dr. Francesco Ferrante and Dr. Riccardo Sanfelice. So thank you for your attention, and if you have any questions, please.